of analyzing atom probe data with your own tools, whatever means necessary. And today we're looking at one of the classical topics in atom probe tomography, which is cluster analysis. There's a whole host of cluster analysis tools out there, and sometimes it can be a little bit daunting looking at what's what and which one is best suited for the purpose. And at the end, we're going to use the one that I've developed simply because it's the simplest one to use. The only thing you need to do is actually press start and we'll do the rest for you. But of course, you need to be able to compare to other methods, and sometimes it doesn't harm to also use what other people have used out there. Essentially, the whole cluster analysis problem is a problem where you have a higher density in a matrix of lower density. Now, this is of course already a bit of a stretchable definition, because what does higher concentration mean on a single atom level is already a bit of a difficulty. And then where the boundary is, where does a lower concentration start, is obviously a little bit of a difficult question as well. So there is no definitive answer where clustering starts or where it ends, which means when you do analysis, you need consistency, but your method might be just absolute definition. The definition that I've come up with which I've put in a paper in order to compare different cluster algorithms, would be that the set of atoms that are clustered is the largest spatially separated subset of atoms for which the complement is random. So what we're dealing with here is what I'd call binary clustering. So we've got some sort of solid solution, and in the solid solution we've got one type of clusters. This is of course the simplest case. You can have multiple types of clusters, which may or may not be containing one atomic species or the other. But the simplest version is, of course, you've got a set of atoms, which does not need to be just one type of atom. So it could, for example, be, recently I've been working on HSLA steels, where you have titanium carbon nitride clusters, and there you will have a look at the clustering of titanium and carbon. It doesn't need to be just one atomic species, okay? It can be 2 or 3 atomic species. But of course, it gets a little bit more difficult if you've got 2 types of clusters, and these 2 types of clusters contain the same types of atoms, which, for example, can happen in superalloys, where you have a whole host of elements, and one forms precipitate A and one forms precipitate B, which may contain the same chemical elements, but they have cluster pre-stages that contain similar elements. But anyway, I hope for you that you're only going to be concerned with the easiest version of it, and then that definition holds true. So you can say that this area here is my clustered atoms, and if I would start here, if I would make a larger cluster, if I would say everything that's in here in the larger circle is part of the cluster, then I can for sure make sure that the rest of the solid solution is random. So we always need to compare our cluster result to random. But if I make that circle smaller, it would still be random, right? And a good cluster algorithm actually makes this circle, or makes the amount of atoms that we assign to the clusters, as small as possible, while the complement of those atoms is still random. The reason why it says spatially separated is just simply because I could take, an atom here that randomly has the same atomic environment as one in a cluster and swap the two, and would give me the same result, but that of course doesn't make any sense, right? So they need to be spatially separated. The simplest way of looking at the whole problem would just, of course, be looking at the separation of the individual atoms. So again, we've got a cluster here, and we've got some atoms floating around here, and we'll say the max from a cluster perspective, of course, the minimum distance from a solid perspective, but from a cluster perspective, which is say if the atoms are closer together, if two atoms of the solid are closer together than this maximum distance, then they're part of the cluster. So if I look at the distance here between two solid atoms here, it's of course larger than the distance between two solid atoms here. It's pretty straightforward, but has the obvious downside that there will just be maybe two atoms that are just randomly next to each other, and I would start counting them as well, and then depending on how large the cluster is I'm looking for, I would start to either randomly connect up some atoms, or your cluster will get some funny tails because they're just randomly in one direction. There's two or three atoms that have the same small distance. But nevertheless, that is actually one of the more popular methods in atom probe tomography. It's been around for a long time, since the late 90s. Especially Jonathan Hyde in Oxford, he's been one of the guys that's been using it for a long time. And this is actually a recent review paper that they've written about that. So you can see it's from 2010/2011, where they've looked into that. So you can just look at sensitive analysis of the maximum separation method for the calculation of solid clusters. And that part already tells you that finding that maximum distance is pretty much what it's all about in this case, of course. Plus also then finding out cluster sizes. So you will see here that, of course, the steps that you have is that you've got your solid cluster, you've got your D max between each two atoms that you can label, and that D max then classifies atoms to be either in or outside the cluster. And then you connect them up to show you what the individual clusters are. But of course, there is also a step. Well, of course, in this case, they included a step where they eroded the surface. So what that means is that you connect up one cluster, and then you have a look at the atoms that are sort of randomly floating around in space close to that cluster, which give you that funny poking out little things. And then just take those out of the cluster, which is the erosion. And the results that you get here is pretty much from simulated data is pretty much what you would expect in this case. So you can see you've got the core clusters, but you've got things poking out from those core clusters. You can see that if you choose the wrong Dmax, you can of course start breaking up the clusters. Because of course inside the clusters you've got random fluctuations as well, and outside the clusters. So now this fluctuation doesn't just come from the physics of the material itself. It also comes from the fact that your atom probe has a detector efficiency. That's why if you want to do cluster analysis and you want to go to the smallest clusters possible, you need the best detection efficiency. So you can see that the distinction here between the D max and the N min. So one thing I should also say is, of course, you pick up random clusters. So what that means is that you pick up those real clusters, but you also pick up clusters that are just random atoms that happen to be close to each other. But of course, because this is a statistical effect, they tend to be smaller, because the probability of N atoms to be close together randomly goes down exponentially. It's because you have the same probability for two to be next to each other, and you have the same probability for the next based on the same data set really. So we need to take care of this at the atom probe data set itself. And if you compare the experimental distribution to the random distribution, you can say, okay, above a certain cluster size, that's where it gets significant, and everything below that we don't account as clusters. And this is what it says here. This is essentially the second axis here is the smaller n min is, so the smaller the clusters are that I can pick up because of the sensitivity of my atom probe, the better it is, right? And so you can see that if you have for this simulated data that is so up there, if you have different detection efficiencies, so 0.37 would actually be our atom probe here as well, our current atom probe. So you can see that if you need to have relatively large Dmaxes for your clusters to be significant. And if you have a high detection efficiency, so 0.5 is pretty much an atom probe without a preamplifier with a straight flight path. So older models usually have the detection efficiency, and these days the leaps with high detection efficiency come actually much closer to that perfect data. So just to say, if you wanted to go to the smallest clusters, that's not really something our machine is absolutely brilliant for, but that means like you're looking at 2-3 atom clusters, something like that, okay? If we're looking at larger clusters, which go towards precipitation, then we're perfectly fine. Yeah, and there's some rigor in how to choose the, with these comparisons between experimental and random, there is some rigor of how to choose that Dmax. And you need to pretty much follow those considerations in order to pick it. So you can't just go and say, okay, my Dmax is this, and I've just picked it because it looks nice. Offspring is not 100% clear. Very often, if you look in a data set like this, where you have like little clusters that are almost little precipitates, almost, then you will see that the different cluster algorithms will give you almost the same result, and you will have pretty much an area of parameters where you would still get the same answer, especially when it comes to cluster densities. When it comes to looking at how much solid is in the clusters, it gets a little bit more, it matters how much you have, how much of those solids you have included and which ones you haven't. But as long as you're looking at the density, the number density of clusters, it's a little bit more robust. So what the downside of that one is of course that that looking at the distance between two atoms and just taking that as the grounds to pick clusters is subject to statistical fluctuations. So the next thought was then to not pick the first nearest neighbor, because in the first nearest neighbor distance, there's always a lot of fluctuation. But if you go to second, third, fourth, fifth nearest neighbor distributions, then the fluctuations go down by quite a lot, because if you have these two randomly next to each other here, then that's very different to the situation here. But if you start looking at, say, the fourth nearest neighbor, so not this one, but this distance, not this distance, but maybe this distance here, would be the fourth nearest neighbor, and you compare it to the fourth nearest neighbor distance of an atom here, first, second, third, fourth, I think you can see that the statistical fluctuations go down a lot. So you actually have to deal with these things a lot less, and that's the next method that people are using quite a lot, which is this one here. So yeah, I haven't downloaded it yet. Maybe we'll just go into the HTML. So this is also from where I used to work in Sydney, which is actually a group that has dedicated most of the atom probe work to cluster analysis, or at least used to, and have really, okay, maybe it's a little bit slow right now with the broadcast running. But this one's, you will come across that name quite a lot, which is called core-linkage algorithm. So this is the original paper. There's now a couple of papers about that out there as well. And this follows exactly that rationale. So you don't choose the first nearest neighbor, but you choose a second, third, fourth, fifth nearest neighbor. Of course, this adds more parameters. With the dmax, all you had was with the maximum separation method. The only parameter you had was the separation, and the minimum amount of atoms you wanted to be in a cluster. Here, of course, you have the distance that you have as a limit, but you also need to pick the distance to which nearest neighbor that should be. To which nearest neighbor that should be actually doesn't change all that much. It's usually 5th, 6th, 7th nearest neighbor, somewhere around there, but it still changes, and it is an additional parameter. Of course, it's called core linkage because there's another step. So you've got this coring step. So what that step does is take all the atoms where the nth nearest neighbor, so the 5th nearest neighbor, is within that threshold distance, and says, okay, these are my core atoms. I'm sure that these actually belong to my cluster. But then it goes and links all the atoms up that are close to those atoms within a certain distance, and it's a linking distance. That's why it's called core linkage. And if you go through all of the Stevenson maths, then you will find out what those parameters should be. So then you've got the enveloping process here with the coring process and the linking process. And so this is an alloy with it's an aluminium, zinc, magnesium alloy. So that's not too dissimilar to some of the alloys that we're working on here. And here you can see the filtering of the smaller clusters and the larger clusters. Then again, if you're just looking at these large clusters here, it's pretty trivial, right? There's not much you can do wrong. But if you look at the really small clusters, it really depends on your. Anyway, it's called core linkage. One very important mathematical thing that you will come across with core linkage and also some of the other clustering algorithms is something called a KD tree. I think we had a little bit of a look into what a KD tree is earlier. So as you can imagine, if you've got very large data sets, you need to calculate a lot of distances. But really the distances that matter are just the distances of atoms that are relatively close to each other. So if you look at an atom that's look at an atom that's around here, it obviously doesn't have much to do with an atom that's over here. So really, it's a rather local search that we do, which means we can use acceleration structures. If you've got smaller data sets, very often it doesn't matter. You can just brute force calculate all the distances and just select out of those. But the good thing about KD trees is you can also select nth nearest neighbor distributions very easily, very quickly. And the way it works is you take all the points that you have and then you classify them. So you count in each direction, x, y, z. Let's just do it for one dimension. And for one dimension, you just order them all into one direction. And then you say, okay, that's the median value. So this is the point that's in the middle of the distribution. And I say, okay, this is a boundary between all the atoms that are left and the ones that are to the right. And to do this for all different directions. So it might not be in the middle, it might be a little bit offset depending on what you're looking at. And then you repeat that process for each subcell as well. And then if you, for example, look at the nearest neighbors of this atom here, you would just start searching within that square and then expand your search to the neighboring squares. And this is how it speeds up the searching process by quite a lot because it knows sort of where neighborhood relationships are. Of course, you don't need to implement that yourself. Most programs will actually have to implement it for you. MATLAB has also a KD tree implementation for you. And that makes the whole searching process pretty quick, even for large amounts of data. I remember when I started doing atom tomography, if you had a cluster search, we had cluster searches running over the weekend. Just simply, partially because the acceleration structures weren't put in place, and the other reason is, of course, that for computers 6, 7, 8 years ago, there was a lot of work on a modern, even. So these are all the these are, well, not all of them, but these are the two most important distance-based approaches. Recently, because computers have gotten a lot faster, there's been efforts to move to geometric approaches. The reason for that is that they give you unique solutions. So the first work in that area came out of Voronoi. I think it might have been 5 years ago now. And what they did was put a Delaunay triangulation into place, or in 3 dimensions, Delaunay tetrahedralization. So what you do is essentially you create a triangle lattice, or in 3 dimensions tetrahedral lattice out of your data set. Sorry, it's not the Delaunay triangle. Anyway, you get a triangulation. And what they did was say if a triangle is smaller than a certain volume or a certain area at the circumcircle, they took the circumcircle, not the volume itself, just because it's faster to calculate. If the circumcircle of those of that Delaunay cell is smaller than a certain value, then these atoms are clustered. Which has the obvious upside that you're not working with first nearest neighbors, so you're getting rid of a lot of those statistical fluctuations, but also it gives you a unique solution, right? If you have any set of points, you can create a Delaunay triangulation, and it's always unique. No, well, it's not exactly true for coplanar things, but the radius of the circumcircle is always unique. And the reason why it's not unique is just if you put 4 atoms in a square arrangement, then you can do the triangulation of in one diagonal direction or the other. So it's only in cases that really don't interest us. We don't have nicely arranged atoms, so it doesn't really interest us all that much. But technically, it's not unique, but we don't care. Of course, it's a little bit of a measuring Delaunay cells is a little bit counterintuitive. So based on that, I'm not going to claim that I came up with all of this, but I changed it around a little bit. Geometric duals. And so the Voronoi cells are simply the areas or volumes in 3 dimensions that are closer to this atom than to any other atom. And the reason why that's a little bit more intuitive is simply because it's a reciprocal of the atomic concentration. So if you look at what the concentration is, and concentration in terms of number density, so that's the classical chemical definition of concentration. Material science, when we talk concentration, usually what we actually mean is mole fraction. Atoms per atoms, it's actually a mole fraction, but we usually call it concentration. Here we're talking about actual concentration. Of course, in a solid material, it doesn't expand too much, and maybe expanding 2% up to the melting point. Then we don't usually have to deal too much with the differences between the two. But just from a mathematical point, you could actually do it with actual concentrations. Is not much more work, but then you have to deal with boundaries a bit more. But anyway. Both things work, but the concentration is amount of atoms per volume. And if you break that down to the atomic level, you have only one atom, right? So the question of concentration is, what volume does that atom take up? And pretty much the volume that the atom takes up uniquely is the Voronoi volume of that atom. Okay, that's where all that comes from. It's really trying to connect that clustering algorithms that we have with these slightly abstract numbers of dmin, dmax, whatever, to atomic volumes or atomic concentrations, because that's something we understand on a materials level pretty easily, right? I think we have a problem understanding that. The other good thing about these approaches is, of course, it gives you neighborhood relationships for free because you've done the Delaunay triangulation already. You know which atoms are neighbors because these triangles, of course, connect neighboring atoms. So if you want to connect up a single cluster with these distance-based approaches, you need to have a look at the connections between those atoms. I mean, they're there from the calculation, but it's a little bit it's not obvious. But here it's pretty obvious which ones are neighbors. The thing that you, of course, still need to do is have a comparison between what's random and what's statistically significant, because that's not a property of the method itself. It's a property of your system. So that's again a decision we need to make. And we do that by comparing the distribution of these volumes to the distribution of volumes of a random solid solution. So same story as before. So originally we know, okay, these are the solid atoms, but then we act as if we wouldn't know where the solid atoms were. We just know how many there are, and we have them randomly in our data set. And what it then get, of course, and that pretty much holds true for the other distributions as well. That you have a volume. You could do it for concentration as well, but for volume is a little bit easier to see, just because the values can get very large if we divide by very, very small volume values. That's the only reason. It's just a bit inconvenient to plot if we go by concentration. So we'll go by volume. If we've got n, so frequency versus volume, then this is a distribution of a random solid solution. This distribution you can get out of mathematical papers or textbooks. By the way, nobody has ever managed to analytically derive it, but it's pretty well known what the distribution is, what it looks like. And if you have clustering, then of course you will have maybe a lot of atoms that have a smaller volume, and then you have some that have a larger volume, so you have some sort of distribution that way. Of course, with the same area under the curve. That's what we don't have here. And if we look at those two curves, then we need to find the point at which we can say that the atoms are significantly clustered, and above which they're not significantly clustered. So we've got the random distribution that we were talking about before, and then we have the cluster distribution that might look something like this. Okay, and maybe I should change color now. And if I then go and subtract this from this one here, this one from this one here, so we do experimental minus random, then you would get a curve that looks something like this. And what we have here is the amount of atoms that are significantly clustered, and that cutoff point here is where the atoms are significant. The chance that an atom, if it has that volume, is not clustered is higher than it is clustered. And that cutoff point is something we can calculate. It's in a system with binary clustering. It's unique, so we don't need to have a long set of methods in order to try and determine what the actual cutoff is. Which is known from the calculation. It gives us that unique value, and from that value on, you'll have significant clustering. Of course, this would apply if our system was infinitely large. Well, it isn't. So for a finite system, of course, this value will slightly move. This value will have a slight uncertainty. The smaller your system is, the higher the uncertainty. And that's something you always need to be aware of. So if you want to look into clustering, especially if it's small clusters and you have maybe not that high detection efficiency, then you need to make sure that the data set's really, really large. As large as it. In this case, the size of the data set actually really matters. You need to get a reasonably large data set. Otherwise, cluster analysis and on that small scale, on a very small scale, doesn't make much sense. And the other fluctuation, the other source of fluctuation is, of course, that the randomized curve always needs to be simulated. So depending on which atoms you randomly pick, if you've got a small system, you will get fluctuation from that as well. And that's obviously not particularly helpful. So always, if it comes to clustering, it doesn't matter what algorithm you use, try to get large data sets. Unless, of course, the clustering is really, really clear and you just want to know what the number densities are, then it doesn't matter all that much. Then based on this, we know what the individual clusters are, or which atoms are part of the individual clusters. And because we have that triangle that fulfill that criterion are actually neighbors. And the atoms that are neighbors and fulfill that criterion form individual clusters. So we can say, okay, these atoms are connected and these atoms are not connected. If you've got a very high cluster density, then there's always the possibility, and it will happen, that some clusters just grow into each other, and then they become indistinguishable from that perspective on. But that's just the nature of the thing. You would need something like a watershed algorithm to actually try and find if you can separate them or not. But that's just the way it is. Usually clusters are not 100% randomly distributed for a reason, because there's some physics behind the clusters forming, but it's not unlikely that they grow into each other eventually, especially when we're looking at precipitates getting a little bit larger. The next thing is of course that we need to look into which clusters are significant, so which ones are just random clusters and which ones are significant clusters. And we can do that by looking into size. So here we've got the frequency again, frequency versus size. And here we'll look for random clusters. Of course, you've got that exponential decay that I was talking about, so you will have a logarithm here. Otherwise, of course, if you won't see much of that exponential decay. And if you've got significant clustering, then eventually, of course, you've got clusters. So that's cluster size. It's cluster size, whatever you're gonna call it. Let's call it S. I don't know. So this is, say, here you've got a cluster that contains maybe 10 atoms. You have got a cluster that's containing 20 atoms. And here you might have a cluster that contains 50 atoms. So random clusters that contain much more than 10 atoms are rather unlikely. Above 20 atoms, it's pretty clear that the cluster is not random anymore. Again, the limit of where that will happen depends on the detection efficiency. So this cutoff point is not actually unique for a certain material. So but it will depend on what the detection efficiency of your system is. Because of course, if you have a low detection efficiency, out of a certain cluster, you detect fewer atoms, but the random probability that atoms are close to each other doesn't really change. That's pretty much always the same. Whereas the statistical fluctuations in the real data, they change depending on your detection efficiency. But then that gives you a cutoff point as well, and this is all the parameters you need for the cluster search. So you know what the cutoff volume is, and you know what the cutoff and min is, and that just pulls out everything for you. And the good thing is this is all automatable, as you can see in those diagrams. So you can pretty easily devise a method where you can just go, okay, what's my what's my min, what's my V threshold, and will give you the clusters. This is of course very important if you use a cluster search to filter out structures in general. Because right now we've just talked about classical cluster search where we've got little particles in some atom probe data set, and we want to know whether they cling together or whether they don't cling together. But you can also use it to pull out any inhomogeneities in your atom probe data. So if you, for example, are trying to model an interface, and that interface has some stuff stuck to it, has some segregation to it, what you can do is use that cluster search and just pull out the atoms that are segregated, and then it becomes pretty easy to model that interface. If you want to have a good interface model to do interfacial access mapping or local proxygrams and stuff like that, then you can use that algorithm, pull out just the atoms that you care about, and then base your model just on those atoms. And that's the other thing why this is pretty important. And especially if you do these things, you don't want to have an algorithm where you need to spend a couple of weeks trying to figure out what your min and what your threshold values are. Just want to be able to click a button and it gives you those density fluctuations, and you can base your analysis on that. Okay, so much for theory. Of course, we've got all of that in code. And what I've done is actually I've added an algorithm called synthesized cluster data. And if you look into that, it's a very simple script, and all it does is you tell it, okay, I want a volume of, say, for testing a little bit smaller, a volume of 50 times 50 times 50 nanometer cubic volume. You can, by the way, also use that to test isosurface algorithms, so it might help you as well, Lucas. And you have a certain density of atomic density. 50 is very typical for deep rock metals. Of course, it would mean we have a detection efficiency of 1. So maybe if you want to simulate a low detection efficiency, you can crank that down, or just add a variable that says detect efficiency. Then we have a cluster density in 10 to the 5 clusters per cubic micron, which is a sort of a very common value. Most clustering values are somewhere between 1 and 100 times 10 to the 5 clusters per cubic micron, so somewhere around there. In this case, a cluster radius I put in is 2, and a background of 1% of solid background. And that then goes and synthesizes the data set. Should only take a couple of seconds. Shouldn't take too long. Well, you can see that it goes of course by volume. It cubes. The scaling is cubic. But yeah, it's not too long. So you can see here now we've got randomly distributed clusters in a volume, and that's something we can practice our cluster search on. Of course, because that's all simulated, you can change the parameters. So we could, for example, go from 2 nanometer clusters, which is, you looked at that data and it was, I think, pretty clear to you where the clusters are, how many there are, and so on and so forth. So you don't need a computer to tell you. But once you go smaller, say 1 nanometer, I'll make it 25 again, so just we don't have to wait for now. Save and run. You can see when it comes to those smaller clusters, then it starts to get trickier and trickier. If you've got the synthesized data, of course, you can compare how many clusters you find with how many clusters we put in there. So it's sort of your own Easter egg search for clusters. And you will see when it gets very small, you will start either picking up too many, or it's essentially, with the data you saw before, I would be highly surprised if you don't pick up the exact number of classes that we put in. Once you get smaller, especially smaller than that, I think it becomes pretty clear that those two numbers will actually start deviating from each other. But let's start with this one here. And what I did first was actually come up with a KD tree. So MATLAB has KD trees implemented, so we can go MDL. So I just called I just stuck with how the MATLAB people called the variable, which is this model for a KD tree model. You can see it's a KD tree searcher. In this case, sorry, which is called solid. Solid equals column equals 2, and we want all four columns. Oops. So now we've just got the solids. If we put a new figure, you will see that we've just plotted the solid now. Just pulled that out. I can do model. Solid. And then based on that KD tree, we can pull out first nearest neighbor distances, second nearest neighbor distances, and so on and so forth. So in this case, we're searching for the first nearest neighbor. Don't get fooled by it saying 2 for second nearest neighbor. The reason why it's saying second nearest neighbor is because it searches for the closest point in the model data of those points. Of course, those points are the same. So the first nearest neighbor would always be 0 because it would just count the atom itself as its first nearest neighbor, and that's why it's always 0. That's why the nearest neighbor count is offset by 1. So the 2 here actually means first nearest neighbor. But it can go obviously into distance distribution. You can see here this one's obviously 0. But we can go and plot the histogram. You can see this is our distance histogram. So these are the individual atomic distances that we've measured here, and they have a certain distribution. And if you want to know what distances would be normal and which ones are not normal, we want to go and compare that to a randomized solid solution. So we'll go. That's a command. Let's call it. And solid equals. And now we'll just take a random sample. That is out of the length of course out of the post file, and the number of entries is the length of the solids. So now with missing one bracket, and we want all entries. And what that now is it's just a random distribution. So all atoms are randomly distributed in space, but there's just as many as in the solid. So if you look at the solid, you can see we've got 8,625 solid atoms, and we've got 8,625 random solid atoms. Now we'll plot that as well. So we'll plot it into the same thing, and we'll go histogram. Oh, sorry. We need to find these values. Index 1, D1, until we go rand. So now we've calculated resistances for the random solids. We can go histogram D1. And now you can see that they have the same color, which is a bit of a pain, but I'll change the color of one of them. Touch face, gray. And you can see that the distances are not the same. So you have some atoms that for the random data, most of the atoms have a distance of about a nanometer from each other, whereas from the clustered data, you've got atoms that are closer to each other than that. And with the same rationale that we had before, you can use this to determine what the cutoff would be, and then you can do your cluster analysis. Okay. But of course, we also have the Voronoi algorithm that I was talking about before, and that is much easier to use because all you need is so I've put it into here, and you will go into clustering wizard and just add all those paths folders to paths, like the folders and subfolders. And here we've got a cluster elimination. So there is one way of doing it would be using the Voronoi clustering wizard here. Then you've got a nice graphical user interface and everything, but you need an X-range file for that, which you may or may not be working with. How to do the brackets? So I'll have to just move. Okay, so I just used it earlier on a commercial project where we did some analysis. But essentially, here you need the solute and you need the POS file. That's all you need. And then you start it off. It's actually parallelized, so it runs on multiple cores in your computer because otherwise those triangulations can get a little bit slow. So especially if you have a large data set, you might want to run that on one of our workstations where it can run on 8 cores or on 16 cores. Okay, index exceeds matrix dimensions. What have we put in that it didn't like? Another thing we learned is troubleshooting. But so much for the. So let's first look into the cursor we get. I know why it didn't, because it wasn't able to find enough clusters to get a statistically significant result. That brings us back to the earlier problem. Now here we've got a really dilute system with small clusters, so it gets a little bit tricky to do that. But here we get a pretty clear result. So you see the experimental distribution of volumes is the blue curve, and the randomized version is the green curve, and it becomes pretty apparent where the cutoff would be. So here that's your cutoff value, and then you can find the individual clusters. Of course, it bugs me a little bit that it died on me. So let's have a look if we can fix that. There's not enough cluster statistics in that thing to make an automated decision. You could still do that by hand in this case, of course, because the clusters, you sorted the clusters that were actually sorted, still sorted okay, but you couldn't do that in a fully automated way in this case. But we can just create a larger data set because it's something that's in the cluster radius 1.5. Let's leave it open. Save. Okay, I think it's done now. Yep. So we've got our larger volume here with the clusters in it. I think that should enable us to do that. So solid, so you can see now we've got a solid atom. Got about 60,000, 70,000 solid atoms. That's a whole lot more than we had before. Again. Of course, the one thing, the other reason why that of course happened is because in this case, all of the clusters have the exact same size. It's because I put them in synthetically and I made them to be all the same size, which is of course unrealistic in reality. That wouldn't happen. You can see here now we've got a reasonable statistics, and we can determine the cutoff point pretty easily. So the cutoff point in this case is here. So if we go, you can look that the cutoff point is at 0.566 cubic nanometers. And here the cutoff point is also pretty clear. You can see that the cutoff point, the n min is 8, probably 8. Let's zoom in. 5, 6, 7. And you can see here the random clusters, they go down exponentially. This is a logarithmic scale here. And the amount of random clusters just goes down exponentially. Yeah. And in a cluster case like this, of course, there's not much of a discussion where that cutoff point then would be. You can see here at this point above 6 or 7, which is not an untypical value. Again, usually for us with a reflectron machine, it might be a little bit larger, might be 8, 9, or 10. But usually above there, you will not get random clusters anymore. If you had a machine with 100% detection efficiency, you would still get random clusters, by the way, of course. So there's, it's just for physical reasons, just because they're actually there in the material. But yeah, this actually gives us a first of the pass. So it tells us, okay, there is significant clustering, which is based on a Kolmogorov-Smirnov equation. You can look into the paper. Have I not added that to my list of published papers in here? Yeah, I can give you that paper. I can just download it. It's called The Analysis of Atomic Distribution Using Spatial Destiny. I think that's probably something else later. Anyway, you'll find everything that we talked about in the paper, including the the cluster extraction and what the curves would look like for simulated data and for real data. And that explains everything we've done here. So in order to look at the clusters themselves, of course, we just need to pull out which atoms they are. And here you've got the clustered atoms. So you've got something that's similar to a POS file where you've got, of course, this is simulated data. So otherwise this here would be mass to charge values. And here which clusters they belong to. So you can pretty easily look up for a certain atom which other atoms belong to the same cluster, or you can use that to color your plot, for example, to give each cluster a different color, or whatever you can think of. Other things would be to look at different cluster size distributions or look at the chemistry of different clusters. So you might have a look into clustering of aluminium and nickel in a superalloy, and you want to know that depending on cluster size, does the chemistry change? It's a very valid question that we pretty regularly ask for all sorts of clustering problems. You can do that by then going and calculating the chemistry for each of those clusters. And just to show you then the results, you can go. I'll just write over the solid variable. So Schedule 3. Clustered atoms. Oops. Oh, I just wrote over the other one. But now you've got your cluster filter data set, and I think it's pretty clear what that should look like. But you can also see for these small clusters, having a very small part of the data set, having just a maybe 25 by 25 by 25 nanometer cube was a little bit borderline. You would still have been able to pull out the clusters pretty well. What would have been a little bit trickier though is trying to find how large they are, because of course your cutoff values would have more statistical fluctuation. So if you want to do things like analyzing the chemistry and analyzing the size, that would be a bit trickier because you don't know exactly where you should put your cutoffs. If you've got a larger data set, you can obviously do that. If you want to play around now, we can go to much smaller cluster radii. So let's say 0.5 and see what we get. So a 0.5 nanometer cluster is of course 2 to the third 8 times smaller. But remember, 50 times 50 nanometers on our leap is a typical data set size. So that's something you can actually expect to get out of your data. So it's not too far away from reality. Of course, we don't get 100% detection efficiency, but then again, you can change the volume for detection efficiency to some extent. So yeah, this is the distribution that we're looking at now. So it's maybe not that obvious anymore that it's not a random solid solution. And yeah, it wasn't able to find enough clusters anymore. So you can see already if it becomes very small, it gets a whole lot harder. But if you look into the distribution of the Voronoi volumes, you can see that this already is almost a random distribution, right? So there isn't many atoms left anymore. We would be able to pull out and say, okay, this is non-random. It gives you sort of an idea of what the sizes are. Of course, if we're talking about 50 atoms per cubic nanometer, that's about 2 angstroms interatomic distance. It's about 2 nanometer interatomic distance, roughly. And we put our cutoff at 5 nanometers. So we put our random decay at 5 nanometers. So this is really just a very small difference anymore. But you can see that there is a difference between random and experimental, but it's just one that we can't properly pick up anymore. If we go to 0.75, somewhere in the middle, I think we should be able to still pick that up. So of course, the good thing about having these reference files is that if you do some cluster analysis, you can play around a little bit and get a feel of what it means to have a certain dataset size, what it means to have a certain cluster size, what it means to have a certain cluster density, and so on and so forth. Must be published papers for you. Oh, and there's a couple of others missing as well, so maybe I shouldn't be too surprised. Okay, we've got our reference data now. Is that it? Yeah, it doesn't have much of a, you can see that there's not much happening there as well. It should be a little bit different as well, at least. Let's see if we can pick it up or not. Of course, the important values in this case are mostly we want to know how much solid is in the clusters, which you can calculate yourself by just calculating how many atoms are in the clustered atoms file as compared to the original post variable that you put in. And the density the cluster density you can get by looking into how many unique values you have here. Okay. So you can see now we're getting clusters, and we can pick them up. They're just pretty small. So most of the clusters are smaller than 25 atoms. So this is already pretty small clusters. But we can pick them up. Let's have a look what the whole thing looks like. So these are these tiny clusters that we have here. But you can already see they don't look as nice and round as before anymore. They have some statistical scatter to them already. But yeah, you can still pick them up. And if you think about it, 0.75 nanometers, that's about 3 to 4 lattice distances. So these are pretty small clusters. Okay, I think that's pretty much it for clustering analysis. I hope you understand how it works and how we would approach it. Is there any questions about it? No questions? Okay. I think then we'll just conclude the tutorial on the clustering analysis, at least on the basics of clustering analysis. At some point down the track, especially those of you who actually do a lot of cluster analysis might have some more in-depth questions, then we will deal with the whole topic a little bit more in depth. But I think this gives you a little bit of an overview of what the limitations are, what we can do, and what the algorithms are we're using. If you want to use maximum separation method, or you want to use the core-linkage method, maybe because you want to compare it to literature, we can, of course, program that in a relatively short amount of time. They are very mathematically or programming-wise very simple methods to use. All right, so that's it for today then, and good luck with classes.